The second step was definition of a fitness function. How do we define a fitness function? And how do we do the parent selection based on this? So a fitness function evaluates how good or bad a result is or a solution is based on what the overall accuracy it provides us. So it checks every individual of your population on the criteria of how good it is in solving the problem. It is computed for each individual and it is application dependent. What do I mean by application dependent? The accuracy or the measurement criteria changes by the underlying structure of the problem that we have. Okay? So if it is maybe a rent generation or a cost of a home generation, it would provide me with a numerical value or a real number. If I'm using some classifier, it would provide me some label. And with labels, I have some different accuracy measurement criteria. Maybe I'm checking true positives and false positives. Maybe I'm checking the overall accuracy. So it depends on whatever application we are using. It's not fixed. Okay, so this is the part that is not fixed. For classification, we may use classification rate as fitness function. Parent selection is done by one of these four methods. We have roulette wheel selection, we have tournament selection, rank selection, and elite selection. In roulette wheel selection, we assign some probability to each of the individual based on their fitness. Okay? So anything that is more fit will have a greater chance of greater probability assigned to it. And anything that is less fit would have a lesser probability assigned to it. So we're using sort of weighted fitnesses where the weight is equals to the probability of it. So anything that has a good criteria has a greater probability assigned to it, let's say 50%, and anything smaller would have a smaller probability assigned to it. Then we have tournament selection. Tournaments can either be binary tournaments or they can be larger tournaments. In binary tournaments, we split our complete space into groups of two, and from each group of two, one of them is selected based on whichever is best. ठीक है? So जितनी भी मेरी सर्च स्पेस है इसको मैंने सारे दोनों के ग्रुप्स में डिवाइड कर दिया है और उन ग्रुप्स में से जो भी बेस्ट है दैट आई कीप and I'll discard the other one. Larger tournaments are based on the same concept. The only difference is that we take 10 individuals instead of 2 individuals. The other methods include rank selection and elitism. In rank selection, we simply assign numerical ranks, and whichever individual has the highest rank is selected for regeneration of next population. Elitism is similar. The only difference is that K slots or some number of slots are reserved in the next generation for the ones that we have in the current generation. So elitism says that maybe you have found some really good solution in the current generation that you might not like to use in the next generation. So we use this individual and this chromosome in next generation as well. This is sort of making sure that we do not lose one good solution that we may have found in the first iteration or in the second iteration. Crossover is the primary operator, and mutation only serves in finding new combinations or diversifying the population. So what crossover does is two parents or two individuals are selected and we combine the chromosomes or the genes of one individual with the other individual. And this chance of combination is somewhere between 0.6 and 1.0. I'll show you graphically as well what I mean here. Mutation has a much smaller probability. Only one gene or one chromosome of any individual is changed at a time, and that also with a very, very, very small probability. Crossover can be done in three ways: either single point crossover, multi-point or two-point crossover, or uniform crossover. Let's have a look at each one of these. In a single point crossover, you select some point in a chromosome or in an individual, and all of the chromosomes or genes of one parent are crossed or split to the next parent. So here you can see that this part is replicated for the next one, but the rest of the part is replicated from the other parent. Okay. So we use the combinations from both of the parents or both of the individuals in order to form the new one. So here we have split or we have changed the genes like this. So we've got some portion from one individual and some portion from the other individual. So the offsprings formed are a combination of both of the parents that we have. This is again what we are doing. We are using some portion of one individual by using some portion of the other individual. So we generate as many set of these as we require using the as many sets of parents as we need. In two-point crossover, we split our individuals on more than one point or more than one. So this part of first parent is used, then this of the second one, and then again this one from the first one. So we're using a zigzag approach over here, and we form the new offspring based on parts of both the parent forms. Endpoint crossover works on the same principle, but you can have any number of crossing over points. And for each crossover point, it would be the same thing. First individual, then second individual, then first individual, then second. A uniform crossover is different from these because we generate a mask. And according to this mask is of the same size as of the parents. And in this mask, some bits are turned on, some are turned off. And then the parents are evaluated based on this mask. So if this is off, if the mask has off value, then the offspring will not have a value corresponding to this parent here. Instead, this value would come from over here. Okay. So for the next one, on bed, second में 1 आ रहा है. So this value would be moved to the offspring. Then again 1, this value would be moved to offspring. Then 0. So this value would not be moved. Instead, we would receive the value from over here. Okay, so in this manner, the mask is placed on top of the parents and then we get the corresponding offsprings. Finally, mutation. What mutation is does it that it changes some gene inside your child or offspring or new population, and it does it is randomly done. Okay, it has any one of these can be selected, and there is a probability according to which this is done. The only objective of mutation is to get a combination that was not possible using the parent chromosomes or parent combinations. The stopping criteria or convergence of algorithm can be based on any one of these. One, the number of generations. If you have generated or iterated the required number of times, then you can stop. Okay, let's suppose 150 iterations कर लिए, so now we can say that whatever the result is, we take as the final result. And second is the fitness value. Okay, you suppose you said that as soon as you have a fitness value greater than 90%, then that is a good enough solution for you. So we stop as soon as our algorithm crosses the 90% mark. So again, that would be considered as a stopping criteria. In case of feature selection, genetic algorithm is devised such that we have the initial population as randomly generated. So any number of features are turned on and any number of these are turned on. Then each chromosome is evaluated on the fitness function, and based on that, the value of fitness function, we generate the next population. Then this population generation process ends when the termination criteria is satisfied, when we have gotten to convergence, and the final solution comes from the best individual in the last generation. So whatever was the best individual in the last generation, that is given out as output. Here is an example where we had those 15 features, and we executed our genetic algorithm, let's say 10 number times. 10 times we executed GA and we saw that how many times which features were selected. So we see that feature number 1 was never selected. We had 10 different runnings of genetic algorithm, but feature 1 never contributed to anything. Same is for feature 2. And feature number 15 and 14 were always selected. These can be safely said as being of most value 12, number 9, 14, and 15. They were always selected no matter which iteration of genetic algorithm I use. So based on these, we can have an assessment or an idea of which features to choose and which to leave out. We can also categorize our features based on which of these are indispensable, which are completely irrelevant, and which are partially relevant. So F14 and 15 were completely indispensable. You cannot leave these out. Feature number 1 and 2 were completely irrelevant. You can drop them out any time, and whatever was in between them is considered partially relevant. It is contributing to your solution, but not as much as the indispensable ones. We'll do a working example of this in our online session, for which you should cover all concepts done in this video lecture.